This is now the third video in applied microeconometrics, and this video is going to be about distribution regression. Remember that in my very first video I said that we are going to talk about quantile and distribution regression, and I have already talked a lot about quantile regression already, but I haven't said anything about distribution regression yet. But that's going to change today. What we can say is that there is an alternative to quantile regression, and that is indeed distribution regression. In order to say something very briefly about distribution regression, that's actually possible because of the fact that we now know that quantile regression, well, what we want to do in quantile regression is that we want to estimate the conditional quantiles. And therefore, it is not that difficult to understand that what we would like to do in distribution regression is that we would like to estimate the conditional distribution. Well, later on I'm going to talk about how we're going to do so, but what we should now realize is that what we have now is that we have two different tools in order to, well, take into account that we would like to estimate at the moment that there is impact heterogeneity. Remember from my very first video that I said that it isn't a good idea to use ordinary squares at the moment that there is impact heterogeneity. And now we have two different tools to take that into account, either distribution regression or quantile regression. The question of course arises, which of the two should you use? Well, that's actually not such an easy question to answer because of the fact that that actually depends on the situation. Therefore, what I'm going to do over here is that I'm first going to talk a little bit about the benefits and the drawbacks with respect to distribution regression. And it's easy to understand, of course, that a benefit that we are going to have with respect to distribution regression is going to be a drawback with respect to quantile regression. And the other way around, of course, at the moment that we have a drawback of distribution regression, then that is going to automatically be a benefit of quantile regression. Well, let me first of all talk about the benefits of distribution regression. First of all, we should realize that it is simpler and faster than quantile regression. In that sense, we do already know, for a long time I suppose, that these days it's not that difficult anymore to do, say, linear regression analysis, even in the case that we have very large data sets. At the moment that we are going to have data sets for even more than 1 million observations, or maybe even a couple of millions of observations, then it's still possible to have many different regresses, maybe 1,000 or maybe even a couple of thousand observations, and then it will still not take you that much time to estimate that on a nowadays computer. However, I will not recommend you to do that at the moment that you're going to do quantile regression. The moment that you're going to run a quantile regression with a couple of millions observations and many different regressors, well, then I have no idea exactly how much time that will actually take, but I would not be surprised if that is going to take you a couple of years. However, even though distribution regression is not as fast as linear regression, it's going to be much faster, so it's more or less in the middle. And the reason behind that, we will see later on, is that, well, distribution regression is actually not anything different from standard logit or probit. So therefore we should realize that, well, there it is actually possible to use large data sets, maybe data sets of a couple of 100,000 observations, or even more than 1 million observations. And also even there it is possible to have relatively many regressors. Maybe not in the thousands, but it is still possible to have many different regressors and not having to wait a very long period of time. So therefore, well, if speed is important, then at that moment in time it's better to use distribution regression rather than quantile regression. Another reason to use distribution regression is because of the fact that sometimes one wants to estimate the distribution rather than a quantile. Later on we will see, well, examples in which we're going to estimate distributions. Now you might of course say, like, well, that's not really a problem because of the fact that we can always use quantile regression analysis. And given the fact that quantile regression actually tries to estimate the well, quantiles, which are the inverted distribution functions, well, what we could do, of course, after doing quantile regression is that we could simply invert the quantiles and then we get the distribution. However, it's of course much more efficient to immediately estimate the distribution, especially given the fact that we do already know that distribution regression is actually much faster than quantile regression. And then finally, you should realize that, well, distribution regression can be easily used when the outcome variable is discrete. Even though I haven't said that yet, you should realize that quantile regression can actually not be done at the moment that you have a discrete outcome variable. Especially at the moment that you have a binary outcome variable, then you cannot do standard quantile regression. The moment that you're going to not have a binary outcome variable, but for example a situation in which we are going to have an ordered outcome variable, also then it is not possible to do quantile regression analysis. However, distribution regression is always possible, so especially at the moment that we have a discrete outcome variable, well then it would be always best to use distribution regression instead of quantile regression. Then we come to the drawbacks with respect to distribution regression, and you can actually say that there's only one important drawback with respect to distribution regression, but it may be a very important one, and that is related to interpretation. It's much easier to think in terms of quantiles and to interpret quantiles and to interpret quantile regression coefficients rather than to interpret, say, coefficients that we get from distribution regression. In that sense, it's good to look another time at an example, and another time the example is going to be log wage regression. Suppose that we have a log wage regression and we're going to do a quantile regression, and at the right hand side, among other things, we're going to have a college dummy. Well, then we do of course already know that at the moment that we, for example, are going to do median regression and the college dummy is going to be equal to 0.4, that means that, well, at the median, the person who is exactly at the median is going to get 40% extra in terms of pay at the moment that that particular person has a college degree rather than not having a college degree. That's the interpretation with respect to quantile regression, and it's quite in line, of course, with standard linear regression analysis. However, at the moment that we're going to look at distribution regression, well, then at that moment in time, we're going to have another interpretation. Then what we're going to do is that we're going to look at the probability that somebody earns less than a particular amount. Suppose that we're going to look at $30. So then what we're going to do is that we're going to ask ourselves the question, what is the probability that somebody earns less than $30? And then the coefficients are actually showing how much that probability is going to change. So then at the moment that we're going to look at the coefficient for college, then that actually says by how much the probability to earn less than $30 is going to change at the moment that you have a college degree compared to not having a college degree. Take into account that that probability usually is going to, or that coefficient usually is going to be negative because of the fact that you expect that the probability will actually go down that you earn less than $30 at the moment that you have a college degree, because college graduates usually make more, so that means that the probability that you make less than $30 will actually go down. Well, that is a lot more difficult to understand than at the moment that we would have looked at coefficients of quantile regression. And that's the main drawback with respect to distribution regression. Now let me go on with distribution regression itself. What is it? Well, the whole idea behind distribution regression is that it's always possible to write the distribution of a random variable y as, well, of course, the distribution of a random variable. Well, in the case that we have a random variable y, can always be written as the thing that we have here at the left hand side. And what we can claim is that we can always write it as, well, this function capital phi that we have over here, where capital phi actually stands for the standard normal distribution function, and that's going to be evaluated in a function mu, and that's going to be evaluated in a value y that's exactly the same value that we had over there, in which we were evaluating the, say, distribution function. And this mu is going to be a uniquely determined function. we're going to look at this, then you might also say that it's always possible to transform a random variable into another random variable, that is mu y that we have over here, which is going to be, say, normally distributed. That looks like a very well general statement and maybe also a very restrictive statement, but actually this statement is very simple to prove. The reason behind that is because of the fact that you should realize that at the moment that we're going to look at, first of all, the normal distribution function, well, that's an upward sloping function, monotonically upward sloping function, and it's, well, strictly upward sloping, and that means that we can always take the, say, inverse of this distribution function. Another thing that we can say about this thing that we've over here is that's also upward sloping, could be weakly upward sloping, but also we do know that it's always in between 0 and 1. So therefore what we can do over here is that we can at least take the inverse of this distribution function that we have here at the right hand side of phi, and then we immediately get that mu y is going to be equal to the inverse of the normal distribution function evaluated in this fy that we have over here. Luckily this thing is in between 0 and 1, and therefore this whole thing is going to be well defined, and of course this is going to be a unique solution. Well, and then what we can do is that we now know that this is always going to be true. Then we can also look at the conditional distribution, of course. We can do exactly the same thing with respect to the conditional distribution. Then we can say that the conditional distribution of y conditional on x can always be written as the, well, normal distribution function evaluated in mu, y, and x. Where now mu is not only a function of y, but also a function of x. And well, what we can always do is here do exactly the same thing as what we did in the previous slide. Well, take the inverse of the normal distribution function at the left and the right hand side, and then we actually get this mu yx over here. So that seems all quite simple. The only problem that we of course have is that this function that we have here at the left hand side is unknown to us. It's the, well, it's the data distribution, and at the moment that we would like to estimate, then we should realize that we never assume as econometricians that we do know the data distribution. So therefore the question arises, how are we able to estimate this mu over here? Because we cannot calculate it, because we do not know this thing that we have here at the left hand side, but could we, well, try to estimate it? Because if we have an estimator of this thing over here, we simply plug it in, and then we get, say, an estimator also of this distribution function. Well, that's actually possible. It's not that difficult because of the fact that what we could do is that we can estimate this with respect to maximum likelihood. At least at the moment that x is going to be discrete. Suppose that we have an x which is discrete, for example, a dummy variable, where x can take only two values, either somebody is a woman or a man, and then what we could do in that particular situation is that we're going to divide our data set into, well, the two different values of dummy variable, 0 and 1, and then we could actually, well, maximize this criterion function that we've over here. This is going to be the criterion function that we're going to get at the moment that we want to estimate this mu hat that we've over here. Even though it's maximum likelihood, you should realize that this is completely, well, non-parametric because of the fact that I haven't made any assumptions about the underlying distribution of this f that we have over here. So the only thing that we need to do is to, well, define this dummy variable that we've over here, an indicator that, well, any, say, observation is smaller or equal to y, so any observation which is larger than y is going to have a 0, and every observation which is an observation smaller than y is going to have a 1, and then we are going to, well, maximize this thing that we have over here. Take into account that this is actually nothing else as, at least what we have here, from here onwards, is actually nothing else as the likelihood function that we also have with respect to probability. That means, of course, that conditional on the group that we're going to look at, the 0 or the 1 group, this thing that we have here at the left hand side is nothing else as the estimation that we're going to have at the moment that we're going to do a probit estimation, but without any regresses. Because this is just one term, it's not a set of coefficients, this is just one term. We only want to estimate one single m that we have over here, or maximize with one single m that we have over here. Now, I do not know whether you have ever asked yourself the question, what are we going to get at the moment that we're going to do a probit without any regressors? Well, then what you will actually get is that you are going to get the, well, standard normal distribution, well, the inverse function of the standard normal distribution, and then evaluate it in, well, the percentage of observations that are going to be having a 1. In this case, the percentage of observations that we're going to have that have a 1, take into account we're only going to look at those observations for which xi is equal to a certain number, 0 or 1, so xi equal to x. So therefore what we're going to get over here is actually nothing else as the percentage of, say, observations that are smaller than y, well, for the subsample for which xi is exactly equal to x. So that's what we are going to get over here now. That's going to be our estimator that we have over there. Of course, we can substitute this estimator into there in order to get an estimator of our distribution function. Well, then it's immediately clear, because of the fact that we have here the inverse and there we have the distribution function itself, the standard normal distribution function, that these two are going to cancel, and that means that the only thing that we're left with is this thing that we have here within the parentheses. Well, we should realize that this thing in the parentheses is actually nothing else as the, well, the so-called empirical distribution function. I'm pretty sure that you have already heard about that before, the so-called empirical distribution function, which is actually a very great function to non-parametrically estimate a distribution function. It's just a percentage of observations for which yi is going to be smaller or equal to y. Well, that is actually nothing new, of course. You should realize that that is something that we already knew, and that has nothing to do directly with distribution regression. However, even though this works pretty fine, you could say, there is a problem with respect to this method. The problem is related to the fact that this, of course, works at the moment that we are going to have an xi that is a dummy variable, so only 0 or 1, because then we simply split up the data into two different parts. But what are you going to get at the moment that xi is not going to be a dummy variable, but suppose that it's going to be continuously distributed random variable? Well, then of course we're going to have a problem, because then we should realize that there will not be any observation for which xi is exactly equal to x. That is by definition the case at the moment that you have a continuously distributed random variable, and you take a particular level x, then no observation will actually exactly have an xi exactly equal to x. So the question arises in that case, what are we going to do about that? Well, another thing that we should realize is that even in the case that xi is not going to be continuous, we can have many different outcomes, such as, for example, h. H is not really continuous, but it is still possible, of course, to have many different outcomes with respect to h. Somebody could be 20 years of age, 21, 22, etc. Also then, if we do not have a very large data set, then we are going to have very few observations for which xi is exactly equal to x. And even in the case that we're only going to have dummy variables, but we are going to have many of them, well then at that moment in time, we're also going to get very few observations, which is of course problematic. So the question arises, what could we do in that particular case? The standard thing in econometrics to deal with that is that we are going to use a parameterization. So far we haven't said anything yet about how this function mu yx is going to look like. We have not specified it all, we had made it completely flexible. However, well, what we can do is that we could specify, parameterize it a little bit. What we could, for example, do is that we are going to say that mu yx, for whatever it is going to look like this thing that we have over here. It's going to be equal to px multiplied by beta y. where px is now going to be some kind of power function of the elements of x that we have included. So that means we can include x, x squared, x to the power 3, etc. It's also possible to use a piecewise constant or a piecewise linear function or even cubic splines over here. We can do it as flexible as possible, but the whole idea is that we are going to make a restriction that mu yx should always look like, well, px multiplied by beta y, where beta y is just a set of coefficients that we're going to get. If we're going to do that, well, then we are going to be in a situation in which we still are going to have essentially the same kind of maximum likelihood procedure as what we had before, but now what we're going to get is that we are going to minimize this function with respect to the beta coefficient that we have over here. But it's immediately clear that at the moment that we're going to maximize this thing that we have over here, then we have exactly the same likelihood function as with probit. So that means that doing here distribution regression, finding this beta y's that we have over here, was actually nothing else as doing a probit regression, where the dummy that we're going to use, the 0, 1 variable, the outcome variable that we're going to use, is actually nothing else as, well, whether a particular observation yi is smaller or equal to this y that we have over there. At that moment in time we have a 1, otherwise we are going to have a 0. So that implies that if you would like to do distribution regression, the only thing that you need to do is doing a probit. But let's look at the implementation. I will start here the implementation with respect to Python. Well, that is what we always do, and here again I'm going to introduce some imports. Well, we already know about these ones that we've over here. Now we are not going to import, of course, quanta regression, but we simply are going to use now stats models for this probit. Then again, what we're going to do is that we're going to introduce these taus over here, even though I'm now actually not interested in the quantiles. So this is not really necessary to do. But I'm interested in the, say, distribution regression, so I'm interested in some particular numbers where I'm going to estimate my distribution. Well, what I could have done is that I could have simply said, like, well, I'm going to estimate this as at $15, at $20, $25, etc. But instead I thought it would be much more, well, intuitive to actually do this at the different quantiles of the unconditional distribution of the wages. So therefore what I do first is that I calculate here the first decile of the wage distribution itself, the wages not taking anything into account, here the first quartile, etc. And then, well, here we have the axis that we're going to include, and then we are going to do for all these different quantiles that we have calculated over here, we are going to now do distribution regression with respect to this for loop that we have over here. And then first of all what I'm going to do is that I'm going to introduce this dummy variable. Y is simply a dummy variable that indicates that, well, the wages, the log wage, should be smaller than the quanta. Here we have this variable that we have over here. I needed it actually in order to get a quantile. And then after that, we do probit. First of all, we define this class that we have over here. And then next to that, we are going to estimate, that is this probit model that we have over here, model fit. Then we get the parameters, we get the standard deviation, and we are going to now, well, store them into result and result1, and we're going to print them. Well, we can do exactly the same thing with respect to R. Actually, in this case, the R program seems to be a little shorter. Here, actually, we don't have to include anything. I have included Haven in order to import, again, the Stata dataset, but actually that is not in this listing. And then, again, I'm going to, first of all, calculate the unconditional quantiles of the wage distribution. And then for all these quantiles, I'm going to, well, first of all, introduce a dummy variable for the wage being smaller than a quantile. Then I do probit. Well, I do the summary in order to get the coefficient, the standard deviation. I store them into result and result1, and I actually print them. Well, then we get the following results. Well, at the moment that we're going to look at distribution regression, then first of all we can look at the constant. Well, with respect to the constant we have more or less the same thing as with respect to quantile regression. We see that the constant always increases with respect to the tau in this case, with respect to the wages in which we are going to evaluate our distribution function. And the reason behind that is because of the fact that, well, first of all, distribution functions are increasing, but a more intuitive, well, way to explain this is that, well, we here calculate or estimate the probability that you're below a certain wage, and of course, at the moment we're going to look at the wage that is exactly the first decile. Well, there are, of course, many fewer individuals that earn less than the first decile than the number of individuals that earn less than the 9th decile. Almost everybody, 90% of the individuals, of course, earn less than, say, the 9th decile by definition. So there we do see that the constants are actually increasing with respect to the quantile that we're looking at. Well, then, in addition to that, we, well, should realize that at the moment that we're going to look at distribution regression, then the interpretation of the coefficients, as I already said, is a little difficult because of the fact that we should realize that actually, well, a positive sign means that the wages generally are lower. It sounds a little bit strange, but what you should realize is that what we estimate over here is the probability that you earn less than a certain wage. That means, of course, that at the moment that you're going to have a positive impact on that, then the probability to earn less than a certain wage is going to be higher. So that means that you must have a low wage in order to earn less than that particular wage. So a negative sign means actually that your probability to earn less than a certain wage is going to go down. That means, of course, that you have a relatively high wage. So it means here to say that, well, a positive sign always means that you have a, say, lower wage that has negative impact on your wage, and a negative sign means that you have relatively high wage. So like what we have seen before, gender means, being a woman means that your wage is going to be lower, and we actually now see that that's true for the whole distribution. It's a little bit surprising here that we don't find any difference anymore at the last decile. What we still found actually at the moment that we were looking at the quantiles. At the moment that we're going to look at education, well, then we still see that, well, college credits, of course, make the highest wages. And then after that, we have the high school graduates, and actually a little bit surprising, again, those that have some college actually make less than the ones that have a high school diploma only. So what we are going to see in addition to that is that even though we see some differences over the distribution, the pattern is not that clear. So we do see that it first increases, but at the last decile, it actually decreases with respect to a college degree. Again, we cannot say too much with respect to the differences with respect to regions, but we can, of course, again, look at Central City. Here we actually do see, well, that Central City has a negative impact on your wages, at least for the lower quantiles. For the upper quantiles, we actually do surprisingly see that there is a positive impact. Again, that could be related to, say, well, the very nice larger cities like New York City, Boston, well, San Francisco, etc. We also see that metropolitan areas actually have higher wages. Well, that's something that we have already seen before when we were looking at quantile regression analysis. Age has a positive impact on your wage, and again we see that it's not linear, and here again we see that there's actually not such a much of a pattern along the distribution. Then with respect to non-white, well, we do see that non-white are, well, being non-white has a negative impact on your wage because of the fact that we have here positive say, coefficients. And again, what we see is that that is less so at the moment that we're going to look at the higher quantiles. And finally, Hispanics have also a lower wage, and we see here no real pattern along the distribution. I would like to go on with the next topic, and that's the topic of counterfactual distributions. Sometimes we want to compare the distribution between two populations. For example, we have already done that when we were looking at the quantiles between women and men. Even though we were doing that with respect to quantiles, what we in fact were doing, that we were looking at differences between the distribution of wages between women and that of men. Well, in order to analyze this a little bit better, we are going to call now the random variables of the two groups YA and YB, and the corresponding distributions are going to be denoted by FYA and FYB. So for example, we could say that YA are going to be the wages of the women and YB are going to be the wages of the men. Well, in addition to that, so far we have only looked at a situation in which we are going to look at the unconditional distributions, but we should take into account that there may be some characteristics that are going to explain, of course, the, say, outcomes of YA and YB. We're going to denote them by respectively XA and XB. So again, at the moment that we're going to look at wages, then XA and XB are of course going to be, well, characteristics, human capital characteristics, such as, for example, education. Well, now based on this, we can say that generally speaking, well, why might there be differences between these two distributions that we have over here? Well, very generally we can say that there may be two reasons why there might be a difference between these two distributions. The first is that it may be the case that the distribution of the characteristics of the two populations may be different. It may be possible that these two, say, distributions of XA and XB are going to be different, and that results in a difference in terms of the distributions. For example, again, if we are going to look at the, say, distributions of wages between women and men, then it could of course be possible, I'm not saying that that's true, but it could be possible that the education level of the women is going to be lower than the education level of men. Well, then it's of course not so strange that we are going to see that generally the distribution of the women is going to be a little bit more to the left as that of men, because of the fact that at the moment that we're going to even look within genders, for example, at the moment that we're going to look at men, then we do of course know that if we're going to compare the high educated men with the lower educated men, then we do know that, well, generally the higher educated men are to the right tail of the distribution function. So therefore we should realize that then it's not so strange to see any difference in terms of the distributions. This was maybe not such a very great example because of the fact that also in the United States, but also, for example, in many European countries, it is the case that now these days, especially working women, are actually higher educated than working men. So therefore, if anything, actually the characteristics of the women in terms of education is better. So therefore, actually men should actually make less than women, or the other way around. Women should actually make more than men if it would only have been for education. Of course, there are also other characteristics, such as, for example, experience, where it may sometimes be different and more in favor of the men. But we can also think of other, say, examples. That's what we're going to do later on. We can also look within gender. For example, we can look at men, and we have already seen before that at the moment that we're going to look at men over time in the United States, that the distribution of men has changed quite a lot. That is to say that, well, compared to 1975, well, we see that in the more recent years, the men that are at the bottom of the distribution actually make much less than they used to do in 1975, whereas those at the top of the distribution, they actually make much more. It could, of course, be possible that this is resembled by the characteristics. It could be possible that the men at the bottom of the, say, wage distribution now have much lower education levels than they used to do in 1975, and at the top they may actually have much higher education levels. All that is possible, and also of course related to the characteristics of the populations. But we should take into account that, well, apart from the fact that there may be differences in the characteristics of the populations, there may be also differences in the conditional distributions. There may be in fact differences in the way that these populations are going to be, you could say, paid for their characteristics. It could be possible that the A and B population, for example women and men, they are identical to each other in terms of characteristics, but then there can still be a difference in terms of the distributions simply because of the fact that for these characteristics these groups are going to be differently paid. The question of course arises, how can we then, well, how could it be possible to, say, look at these two different things that we've over here? This is important because of the fact that you should realize that at the moment that we're going to look especially to the differences in wages between women and men, well, then you might of course also think in terms of discrimination. Well, if we can show that most of the, say, differences between women and men are related to characteristics between women and men, well, then you might say, like, well, even though there are differences, maybe discrimination is not the most important reason. However, at the moment that we will find that most of this is going to be related to the differences in conditional distributions, well, at least the differences in the conditional distributions could in fact be related to discrimination. That's not directly clear because of the fact that we should realize that the differences in the conditional distributions could actually also be related to differences in what we could say unobserved characteristics, differences for example in talents. I'm a little bit skeptic with respect to that because of the fact that if we're going to see that even in 2022 there was a difference of 20% in the wages between the women and men over the whole distribution, well, it's hard to say that that could be actually related to differences in talents when we actually do see that there are hardly any differences in terms of the characteristics between the women and men. But an interesting question in general of course arises, could we actually say what these two things are? For example, at the moment that we're going to compare women and men with each other, but also at the moment that we're going to look, for example, over the last 45 years and we're going to look at within gender. Well, we can do that by using a very famous trick in statistics, and that is the law of iterated probability. Generally, we do know that any kind of distribution function, this is the unconditional distribution function, in this case of the A population, can be written as, well, an integral over the characteristics of the, say, A population, and then, well, we integrate over the distribution that we have, the conditional distribution, so no longer the unconditional, but now the conditional distribution, and then multiplied by the density of those characteristics. This is actually quite intuitive. What you should realize is that this actually says nothing else is that the distribution function in any y that we have over here can actually be calculated as being the weighted average of these conditional distributions. And you should realize that these conditional distributions of course shift for different values of x. In general, we can, for example, expect that for higher educated individuals, this distribution function looks, well, is a little bit more to the right than at the moment that we're going to look at low educated individuals. And what you should realize then is that what we do is that we multiply this by the percentages, essentially, that we have within that particular distribution with a particular characteristic. So that means, for example, that if we're going to look at a, say, population that has, for example, very many high educated individuals, well then at that moment in time this whole distribution function is going to shift to the right because of the fact that you get a relatively high weight for those distribution functions, those conditional distribution functions that are relatively to the right. The moment that there are very few high educated individuals, then we're going to get a shift to the left. So that is something that you should actually realize? Well, this we can do with the A population. We can do exactly the same thing with respect to the B population. But then we can even ask ourselves the question, could we actually look at a random variable where essentially an outcome variable, essentially a population, a counterfactual population, where the, say, A population is going to have the characteristics of the A population, but the conditional distributions of the B population. So one thing that we can, for example, ask ourselves the question, could we in fact look at a situation in which we're going to look at the women, we're going to look at the characteristics of the women, but they are going to have the conditional distribution of the men. Another way of saying this is that we're going to look at the women being paid like men. That's interesting to actually do because of the fact that then we can make a comparison with the distribution of the men and the women itself. Question of course arises, how can we actually do that? Well, based on the idea of, well, the law of iterated probability, we can actually construct such a, what you could say, counterfactual population. Well, let's call this counterfactual population, something that we of course not observe. Let's call that population the AB population. And YAB is now going to be the outcome variable for that AB population. So then the distribution is of course this FYAB that we have over here. And, well, by construction it's going to be equal to, well, the integral over the characteristics of the A population, because we have here the characteristics of the A population, and we are now going to integrate over the distribution function of the B population, but still of course with respect to density of the A population. This is by definition now going to be the distribution that we are going to expect at the moment that the A population has the characteristics of the A population, but is paid in terms of the B population. Well, we can do that of course by using distribution regression. What we could do is that we could use the transformation of distribution regression, then this thing is going to look like this thing that we have over here. It's exactly the same, but now of course we're going to replace this distribution that we have over here by this distribution that we have over here, where we of course now have these coefficients of the B population over here. Well, then we should realize that this actually is nothing else as a population mean. It's a population mean over the A population, not of the B population, because of the fact that we should realize that everything which is random here inside is related to the A population. Even though we do have the coefficients of the B population over here, well, these are just, well, given parameters. These are just parameters. They have nothing to do with the, well, essentially stochastics. So therefore, these are just given parameters, coefficients, that are going to be multiplied, of course, with these x's that we have over here. But these x's, of course, are stochastic. So therefore, we can also write this now as a mean. We integrate here, of course, over the characteristics of xa, a mean over xa with respect to this thing that we have over here. Why is this important? Well, this is important because of the fact that since this is a population mean, we can of course not calculate this, but we can try to estimate this. Population means can always be estimated consistently by the corresponding sample mean, so then what we're going to get is summation over the whole population and dividing by the, say, number of observations that we have. So therefore, our estimator now is going to look like this one that we've over here. Of course, there's still one additional problem, and that's this beta that we've over here. This beta, of course, is unknown to us. But what we can do is that we can replace it by an estimator. What we can do in the first stage is that we're going to run a distribution regression of, say, of the B population in this value y that we're over here in order to get this beta hat by. And this is going to be very valuable. That means, of course, that now what we're going to get is an estimate of the population or of the distribution in the case that the A population is going to be paid like the B population. Well, now let's look at the following situation. Take into account that I started with saying that what we want to do is that we would like to make comparisons between distributions. We would like to look at, for example, the difference between two distributions. We have now two different populations, the A and the B population, and these are their distributions. And one of the things that we can do is simply look at their difference, whether there are any differences between these two distributions in, for example, a point y that we have over here, where we can of course look at many different values of y. Well, looking at this difference is already interesting, but what we can do is that we can rewrite this a bit. What we can do is that we can subtract and add the distribution of YAB from this. Then of course we get 4 different terms, and what we should realize now is that we can now take these two terms together. These two terms are usually called the composition effect. We can also take these two terms together, and that is usually called the structural effect. Let's first focus on the composition effect. What is this? Well, this is the distribution of the B population. You could actually say this is the distribution of the B population with the characteristics of the B population, and of course paid as the B population. That's this distribution that we have over here, minus the distribution of the, say, A population, but paid as the B population. That means, of course, that the difference that we have over here is only related to characteristics. Here we have the distribution that is still determined by the characteristics of the B population. However, this, say, distribution is related to the distribution of the A population, but the payments are still the same. That means, of course, that this difference is related to the characteristics. We usually call that a composition. That's the reason why we call this the composition effect. At the moment that we're going to look at this difference that we have over here, well, then you should realize that this thing that we have over here is the, say, A population paid as the B population, and this is the distribution of the A population paid as the A population. That means, of course, that in this case the characteristics are exactly identical to these two populations that we have over here. The only difference is in terms of payment. Here the individuals are paid like the B population, and here they're paid as the A population. That means, of course, that you could actually see this as a difference in payment. Well, we could call this the payment effect, but usually this is called the structural effect. Of course, we can look at the differences in distributions, but what we could do as well is that we could also look at differences in quantile. We can do that in exactly the same way as we have done so far, by simply taking quantiles. Of course, the quantiles of the B and the A population can be done directly from the distribution function by simply inverting them. But also, we can do exactly the same thing for respect to the AB population, because of the fact that what we can do is that we can calculate this counterfactual distribution for many values of y, and then just simply invert it. And then we are going to see as well that the difference in quantiles between the A and the B population can be subdivided in a so-called composition effect as well as a structural effect. Well, let's now look another time at the implementation. Again, we will start with Python. Well, what I'm not going to do over here is that I'm going to give you the whole list. Of course, everything can be downloaded from Brightspace, but I'm going to only look at some aspects of the code. First of all, we're going to look here at the variable list. That's this thing that we have over here. And then we have here two populations. Unfortunately, I've here called them the 1 and 2 population rather than the A and B population. What we're going to do over here, first of all, is that the 2 population is always going to be the population of 1976. So the start year of our analysis with respect to the CPS, as we'll later on see. And then what I'm going to do is that I'm going to run over all the different years, and I'm going to calculate 3 different quantiles. This is actually a class that I have to define. That will be on the next slide. But first of all, we're going to look at the quantiles of the population where, well, individuals are, say, have the characteristics of the 1 population, and they're going to be paid like the 1 population. That's a population that we have over here that actually changes every year. So that is not necessarily 1976, but it could be 77, 78, 79, etc. And then in addition to that, here we're going to look at the individuals that are actually having the here the payments of the one population, but they're going to be having the characteristics of the two population. And here we have individuals that have the, say, payments of the two population, but they are going to be having the characteristics also of the two population. So this is just the two population, and the only real counterfactual that we're going to have over here is this one, where, say, people are paid like the one population, but they have the characteristics of the two population, of the original population that we had over there. And then we are going to here, well, formally calculate those quantiles. How are we going to do so? Well, that's actually at the next slide. Here I have introduced a class. Classes are actually very nice with respect to Python. You can do object-oriented programming. I'm not sure whether you have ever heard about object-oriented programming before, but as soon as you have done it once, then actually you're going to start to like it. Nice thing with respect to objects or classes is that you can actually, well, classes themselves have their own variables. So in this case, for example, this variable over here is going to be a database for that particular class, for the one population, for the two population. Here we have the variable list. We even have tau over there. And very nice with respect to classes, they also have their own functions. This is a function that is actually, well, very important because of the fact that there I actually do the counterfactual distribution. First thing that I do is that I'm going to introduce a dummy variable that indicates that the log wages are going to be smaller than this y that we have over here. Then what we're going to do, that's the same y as we have actually here in the argument of the function. Then we're going to do a probit. Well, actually the real probit is done over here with fit. And then we're going to store the beta coefficients. Well, and then the next thing that we're going to do is that we here actually are going to, well, estimate the counterfactual distribution. That's actually exactly this formula that we have over here. So this is a mean, so that's also the reason why I actually do have a mean over here. And I simply, well, multiply the x1, which is from the two population, with the beta coefficients of the one population that we have over there. Well, this would be the counterfactual distribution, but I'm not really interested here in the counterfactual distribution, but I wanted to calculate the quantiles. That means, of course, that I'm actually looking for a y that, say, makes this counterfactual distribution exactly equal to tau. That's what I'm looking for. Well, that I can do, of course, by trial and error, but I'm going to search that root that we have over here. I'm going to search that in this case by bisection. I'm not sure whether you know anything about bisection, but that means that we're going to have a very low value, we're going to have a very high value, and we do know that the root is somewhere in the middle. And then what we're going to do is that we're going to make the difference smaller and smaller and smaller up to the moment that we exactly find a y for which this thing that we have over here is going to be equal to 0, exactly the quantile that I was looking for. Well, we can of course do this in Python, but we can also do this in R. Well, this is almost identical. Here again, we're going to have our variable list. Here we're going to have the different years. We are going to, well, have a for loop over the different years. Here we're going to, well, initialize the different quantiles, essentially the different classes that we're going to have. And here we calculate those quantiles and we are going to print them. Question, of course, arises, how are we going to implement the classes? Well, actually, in standard R, there are no classes. But fortunately, there are, of course, extensions of R that do have classes. And, well, now these days, a very good, say, extension is the so-called R6 class. That is almost identical to classes that we have in Python. Also here you have an initialization, exactly the same way as you actually had over there. And well, we are going to have our function. That's also exactly the same as what we had before. Here in this function, we are going to define our, say, indicator. Here we are going to do the probit. Here we're going to do our, say, we are going to store our coefficient. And here we are going to essentially do our, well, this is in this case the calculation of the counterfactual distribution. And here again we're going to have that counterfactual distribution minus, say, the tau that we have over there. And here we calculate the quantiles. Well, of course, I have done a very, well, nice job, I would say, by programming this in R. I'm myself a little bit more into Python, but I do like to program these kind of things also in R. But, well, there's also other code available in R, and that actually comes from BlastMalie. On his website, you can actually download R programs that actually also do counterfactual distributions. BlastMalie, he actually looks a lot at counterfactual distribution, like actually myself, and well, he does have a lot of code doing counterfactual distributions actually in R, but you can also find it in Theta. That brings me to the application. Another time we're going to look at the CPS, and in this case what we're going to do is that we're going to look within genders and over time. Remember that at the moment that we were looking at the first quartile, that at the moment that we're going to look at males, that there was quite a big drop with respect to the first quartile, actually also with respect to the first decile, but here we're only looking at the first quartile. Then we see that there is a quite big drop with respect to the wages at the first quartile over time. That was especially true in the 80s and the 90s. Here it's with respect to, well, 1975. There was a big drop with respect to the wages in the 80s and the 90s. There was a small recovery, or, well, somewhat of a recovery around the turn of the century, but then around the period of the global crisis, we do see that there was a big drop again. More in the recent years, there is a very sharp recovery, but at the moment that you're going to look here in the year 2021, then we see that the wages are still substantially lower in real terms in 2021 compared to 1976. This is still around 8–9%, and that's of course quite a big drop, taking into account that there's here a, say, 45 years difference. So nowadays, still men make almost 10% less than they used to do 45 years ago. And the question of course arises, well, is this related to the composition of the workforce? Did men simply become less, well, good in terms of their characteristics? Or is it related to the structure? Did men get paid worse over time? At the moment that we're going to look at the composition, then we do actually see that the composition effect is, well, apart from this very start that we have over here, it is generally positive. And it's actually not that small either. It looks maybe a little bit small, but you should take into account here, it is still almost 10%. So that means that, well, if it would have been only for the composition, then men should actually earn, well, over this whole period of time, including right now, they should actually have earned more in real terms than in 1976. The question, of course, arises, why was that the case? Well, this is completely related to the level of education. Men here at Q1 increased their education level over time. So in 1976, take into account that these are men that are actually at the bottom of the wage distribution. Most of these men were, well, most of them, they were at most high school graduates, and many of them, they were even high school dropouts. But now these days, well, you would say that, well, actually, there are now men, even at Q1, that are college graduates. Maybe still not many of them, but take into account that the amount of college graduates has increased over time in the United States, even including here at the bottom of the distribution. But that implies, of course, that all this decrease that we have over here, given the fact that, well, the composition effect plus the structural effect always have to sum up to the total effect, that means, of course, that the structural effect should be even more negative than the total effect. And that's exactly what we see over here. We see here that the structural effect is everywhere below the total effect. So that means that the reason why men actually had this drop in terms of wages can be fully ascribed to the fact that they were actually paid worse over time. The question, of course, arises, why might this be the case? Well, this has all to do with the, say, increasing so-called college premium over time. There has been written a lot in the United States about this increasing college premium over time, but even here in Europe, well, there has been an increase, a large increase with respect to the college premium. And this increase in college premium, essentially in the United States, doesn't come so much from the fact that people that have a college degree have increased their wages, but it was much more related to the fact that those without a college degree have decreased their wages. That's of course possible, right? You should realize that at the moment that the college premium is going to increase, that means of course that there is a larger difference between, well, the wages of individuals that have a college premium with those wages of individuals that do not have a college premium. Well, that can actually increase, first of all, because of the fact that, of course, men that have a college degree are going to increase their wages over time. But it can also be the case that, well, there is a drop of the wages of the men that actually do not have any college. And you should realize that the majority of the men that we have over here, especially in the earlier periods, well, they did not have a college degree, of course. So therefore, we see that their wages have been dropping over time, and, well, that's exactly what we see over here. Most likely, that has to do something with computerization. These, well, men were actually substituted by computers and machines, and therefore, it is the case that their wages have dropped so much. The moment that we're going to look at females, then we see a completely different picture. At least at the moment that we're going to look at the, say, total wages, well, they actually have been increasing over time. They have been especially increasing since the year 2000, here around the year 2000. This period not so much, but the most recent years there has been quite an enormous increase in terms of the wages, in such a way that, well, even here at Q1, the wages of these women here at Q1 were in 2021 about 25, maybe even 30% higher than they used to be here in 1975, in real terms. And again, the question arises, is this due to a composition effect or a structural effect? Well, here you immediately see that the answer to that is actually both of them, especially up till 2000. Well, there wasn't that much of a wage increase over that period in time, but it was mainly related to a composition effect. Again, that is completely related to the fact that women, even more than men, increased their, say, education levels over time. We see that this composition effect increases quite a lot in the period before 2000, but it even increases further in the years after that. So therefore, there is quite a large composition effect over here. But you should also take into account that the structural effect has become more important over time and also can explain some part of this wage increase that we have over here. Originally, it was completely negative, but around the turn of the century, it turned positive, and, well, it stayed, well, stable for a while, but in the most recent year, it has increased quite a lot. And therefore, actually, it explains more of the wage increase here in 2021 than even the composition effect. Let's now look at the median. The moment that we're going to look at the median for men, then we see more or less the same picture as what we saw for Q1, for the first quartile. However, everything is a little bit less dramatic. We do see that wages actually have decreased for a while, up till, say, the late 90s, then it increased again, then it decreased again, and it has increased exactly the same way as in Q1, but we do see that, well, at the median, men did increase their wages, well, slightly over here. In 2021, it was exactly the same as in 1975. So therefore, you can say that at least they haven't decreased their wages, their real wages, but they haven't seen any increase either. Again, we see that there is a positive composition effect. So again, this is related to the increase in education levels of these men. More men have now a college degree, and that explains this positive composition effect. In addition to that, we do see that, again, the structural effect, well, is going to be more negative than we see with respect to the total effect. So again, we can say that the reason why we had this drop in terms of wages, again, was related not so much to the composition of the workforce, because that only became better. It's related to the fact that men were paid worse over time. Now going to look at women, then we actually do see that women actually increased their wages by quite a lot at the median. They increased it for over 40%. And now we are going to see that even though the composition effect still is quite positive, indicating that women became more educated, there is also, and most of this increase is now related to the structural effect. Then finally we can look at the third quartile. If you're going to look at the third quartile, then actually we see for males that even though not that much was going on here up till 2000, but males over time have increased their wages quite substantially here at the third quartile. This doesn't look very substantial, but that's because of the fact that I used here the same y-axis for men and women, and therefore this doesn't look that much, but it's still 20%. 20% wage increases, real wage increases over time, it's not nothing. We also see that this is actually not related at all with the composition effect, because of the fact that the composition effect is virtually equal to zero. Question of course arises, why might this be the case? Well, this is not because of the fact that these men here at Q3 were very low educated. That's not what it is. You should realize that this is actually about changes in the wages and changes in the composition. You should realize that most of these men, given the fact that they're at the highest part of the wage distribution, they were already high educated, they did already have a college degree in 1975. So therefore, well, they still had of course a college degree in 2021. Therefore, there was not really a composition effect because they didn't change their composition. They were still having exactly the high education level that they started with in 1975. And that's the reason why we do see that the total effect is completely, well, is almost identical to the structural effect. We see more or less exactly the same thing for women. However, of course, for women now we see such an enormous increase with respect to the wages, which is even larger here than, well, it's about 50% over here. Also here we don't see any composition effect, and that implies again that these women, well, they did not have low levels of education, but they did not change their education level too much. They were already very high educated. We do see that again, the structural and the total effect are more or less the same.